Here's a review of stoichiometry. We use stoichiometry to predict the amount of reactants that are needed, the amount of products that are made, and we start with a balanced equation. So the balanced equation helps us to make associations jumping between one part of the reaction and the other. So we recall that 1 mole is equivalent to 6.02 times 10 to the 23rd particles, ions, electrons, molecules, atoms. 1 mole is equal to 22.4 liters of gas only at STP, which is a temperature of 0 degrees C and an ATM of 1. 1 mole of any substance, ion, electron, is equal to its molar mass in grams. So to use dimensional analysis, you should figure out what you want to know and what you're given, and then bring together a set of conversion factors that rely on these molar relationships and the coefficients between the species in a balanced equation. Species is a fancy term that means nothing but the stuff in the equation. So here is how I would like to set these up. The problem says how many moles of oxygen gas, that would be what we want, are unknown, are required to react completely with 10 moles of hydrogen gas. That's our given, what we know. You write what you want to know, the number of moles of oxygen gas, and set it equal to what you do know, 10 moles of hydrogen gas. And then you multiply it by an equivalency, in this case, using the stoichiometric coefficients of the balanced equation. One rule to note, you must get used to writing the number, the unit, and the compound in each step along the way, because they will help you to keep things straight when you get a little confused. The unit and the compound from the first step must go on the bottom step of the next compound, and you use a relationship that will get you closer to your goal, which is moles. This is a one-step problem. Let's look at a problem that is a little more complicated. Or let's jump all over the page. There we go. Mass to moles. If 27 grams of hydrogen gas react with an excess of oxygen gas, how many moles of water will be produced? Here we go with what we know. This is our given. And what we want are moles of water. And here is our balanced equation. I would like to know the number of moles of water equal to what I've been given, 27 grams of hydrogen. So I start out with this unit and compound. I know it must go to the bottom of my next step, and I can see that I need to transfer grams to moles of hydrogen so I can make the stoichiometry step, which is moles to moles, to get me further to my goal, moles of water. So 2 grams of H2 is equivalent to 1 mole of hydrogen gas. This mole of hydrogen gas must go on the bottom of my next step. I can relate the moles of hydrogen gas to the moles of water. That equals what I would like to know, so I know that my problem is done when what I'm left with on the top part of the problem, the unit and the compound, is equal to what I'm looking for. Now it's just a little math. Multiply everything on the top, divided by the bottom, and so you would have 54 on the top, divided by 4 on the bottom, and that would give you 13 moles of hydrogen gas. And here is the longest problem that you will encounter, and that is a mass-to-mass problem. If 27 grams of hydrogen gas react with an excess of oxygen, what mass of water will be produced? Okay, so our wanted is the grams of water, and our given 27 grams of hydrogen gas. You can see that I'm using the same thought process. In fact, this is the exact same problem. All we've done here is add one more step. Now we go from moles of water to grams of water and get our final answer. Here is a it's very annoying. Here is a practice problem for us. How many grams of oxygen are required to react with 2.2 moles of NO in the production of nitrogen dioxide gas? Well, we need to start out with a balanced equation. So we have NO plus O2 gas yields NO2. Balancing that would require me to put these coefficients in place. I would like to know, I want, how many grams of oxygen are required to react with 2.2 moles of NO. My next step is to put moles of NO on the bottom, and then something that will get me from NO to what I'm looking for, O2. And that would be moles of O2. Okay, using the coefficients from the balanced equation, I see this relationship. It takes 2 moles of NO to react with 1 mole of O2. My next step must have, since moles of O2 is not my goal, I need to move on. So my next step must have moles of O2 on the bottom and some relationship that gets me to grams of O2. Certainly, I can use the molar mass of 1 mole of O2 to find the number of grams. I multiply 2.2 times 1 times 32, divide by 2, and I will yield 35.2 grams of oxygen for my 2.2 moles of NO. The last problem, how many grams of iron can be produced from 100 grams of Fe2O3? This is a decomposition reaction where Fe2O3 decomposes into its elements. When this is balanced, it looks like this. So I want to know how many grams of iron can be produced from 100 grams of iron 3 oxide. On the bottom of my next step, we'll go grams of iron 3 oxide. I am going to go from grams of iron 3 oxide, and then using my stoichiometry step, I will relate the number of moles of Fe2O3 to the number of moles of Fe, and then finally change moles of Fe to grams of Fe. So 104 grams of Fe2O3 is the molar mass of 1 mole of Fe2O3. And I know now that in my stoichiometry step, moles of Fe2O3 go on the bottom, and I know this because whatever's on top on this step will go on the bottom of this step. And I'm relating it to moles of iron. According to my balanced equation, 2 moles of Fe2O3 will produce 4 moles of iron, and 1 mole of iron has a molar mass of 56 grams. That means 108 grams of iron will be produced.